Okay, so let's finish off where we left off yesterday. So we were doing question 9, and question 9 we solved that the gradient vector, the gradient is 1 and 1/2. And then part F here says find the slope if the skier is moving in a particular direction, southwest. So that's the direction of -1 and -1. So basically, the setup of this type of questions is you have a function of fxy, okay, and then we were able to find that the gradient of f, which is basically just it's a vector of f of x and f of y, right? Two partial derivatives, and then so at this point, when we look at, this is basically the contour map or bird view. So basically at this point, we're saying, like, let's say at the point was, I think it was 20 and 10 coordinates. So let's say 20 and 10. At this point, the gradient is, so the gradient at 2010, we solved it to be 1 and 1/2. So basically, we would go 1 this way, 1/2 that way. So that is your gradient vector, meaning that if we're going from, at this point, if we go towards this direction, we experience the maximum increase in slope, or rather in height, in change in height, right? So we're going up, we would be going uphill this way. So there's another element to this, and it's what the question is asking for. The question says, excuse me, if the skier doesn't go towards this direction, right? That's the direction of the gradient. If the skier instead going downhill, which makes sense, if it goes downhill this way, and this is basically 1 and 1, meaning that the skier is going directly southwest, right? Going down by 1 unit and going to the west by 1 unit. So now the question has introduced another factor, or another quantity here, u, which is the vector of travel, right? So this will be -1 and -1. This represents the direction of southwest. So now the question asks for what is the slope going down that way. So meaning, what is the change of what is the change in elevation, rather, going that way. So then now what we're looking for is not it's not the derivative of f with respect to x or with respect to y. Rather, it is the derivative with respect to a vector u being this vector here. Okay, so now the way to do this is intuitively, if we think about it, is at this point here. So I'm going to use a different color. So at this point here, right, this is your starting point. This is the gradient, the direction of maximum increase in elevation. So if we go this way along the direction of the gradient, that is obviously when we experience the maximum change in elevation. Now, if we go in any other direction, we will not. If we go in this direction, that direction, or this direction, we will not experience maximum increase in elevation. That part should be obvious, right? That's obvious. So, so basically, what this equals to, what this directional derivative equals to, this is called directional derivative. This is simply equal to actually, no, let's not writing that. So this is simply equal to f of x at x0, right? Meaning x0 is 20, right? Because we're looking at this point here. This point is 2010. Excuse me. And let's call this two things ui and uj. Okay, so let me restart again here. So in this case, the directional derivative of the function at x0, y0, in this case, this is 20 and this is 10. This is 20, that's 10. So this equals to f of x at 2010 times ui. Okay, ui being this ui here, plus f of y at 2010 times uj. So this is like saying intuitive interpretation of this here would be, we're sitting at this point here, and at this point, if we move by a tiny little bit, right, in the direction of the gradient, if we move by a tiny little bit, then the rate of change is basically the gradient vector coordinates, or the elements, which is 1 and 1/2. But then if we move not in that direction, but rather we move in this direction, going southwest direction, then we have no choice but to really use this value. We assume that at this point, if we move in any direction by a very, very small distance, this is kind of like the magnitude of change that we will experience. So if we're going down southwest this way, then basically this is the default rate of change by the function, right? And then that is going to be built into the rate of change, whatever rate of change you will experience. So then this is basically a way of combining this is the characteristic of the underlying function, combining that with the characteristic of your direction of movement. Okay, so then that will just become, this value here was 1 times the direction of, in the I direction, your direction going along the I vector was -1, and your gradient vector here is 1/2 times your directional vector element here for j is -1 as well, right? That's -1 and -1. So this gives you -1 minus 1/2 equals -2/3, meaning that you're experiencing a slope decrease, or you're experiencing a decrease in elevation by this much. And that's how you approach these type of questions. The key is this step here. Just remember, there's not much to it besides the procedure that you would follow. So the directional derivative for this function, for any function, would just be, so first you would solve for the gradient vector, right? Meaning that this is f of x and f of y. And then this directional derivative just equals to f of x times ui plus f of y times uj, where u equals to ui uj. And once from there on, it's just algebraic operation, and then the end you will get, obviously, the way it's set up, this is kind of like the dot product. So you will end up with a quantity representing the rate of change in this direction here. Okay?